Okay, so on the surface of it, this question seems quite similar to the previous questions. However, there are some subtle differences. So this time they've given us the angle of approach, and they've also given us the angle of deflection, and they've also given us the initial velocity. And the first thing they want us to do is calculate exactly what the basically what the speed is after the first collision. So what they mean by the speed, incidentally, is they mean this speed here. Okay, so the hypotenuse, the magnitude, you know, you get the idea. Right, so what I'm going to do, I'm going to take a slightly different approach on this. I'm going to start by looking at just the horizontal component of the approach speed. So that was 2 meters per second, that's 30 degrees, which means that this is going to be 2 cos 30 degrees. Okay, now because the impulse is vertical, in this case, it means that that particular speed is not going to be affected at all. Okay, so that's still 2 cos 30 as a value. Now that might be true, but there's another way of calculating that, if we knew what V was, because that's 15 degrees, which means that is also V cos 15. So we've got two ways of calculating the same thing. So V cos 15 is equal to 2 cos 30. Well, we can rearrange that, can't we, to figure out what V is. Okay, so if you do that, hang on, so let's you get 1.79. So V is 1.79. 1.793 meters per second, which is actually what we'd expect, right? Because this was 2, and now we have V. Alright, so that's part A taken care of. Now for part B, I'm going to try and do this over here if I can get enough space. Right, so part B, I want to look at just the vertical components now, because that's the bit that E actually has an effect on, right? So this vertical speed here will be 2 sine 30, whereas this vertical speed here would be 1.793, because that's V, sine 15. Okay, well, from that we can calculate exactly what E is, because E should be the speed afterwards divided by the speed of approach. So 1.793 sine 15, and then I divide that by 2 sine 30. Well, 2 sine 30 is going to be 1, right? So it's going to stay as 0.464. So E is equal to 0.464. Right, then moving on to part C. So for part C, we're talking. It basically wants us to calculate the speed now of the second collision. So after the second collision, I should say. So we've got this coming in here. We know what this angle is because that's 90 degrees. That's 15 degrees, which means that's 75 degrees. And we know the speed is 1.793. So all we're going to do is split it into the component vectors. So this one here would be 1.793 cos 75. And we can work out what that is, right? So 1.793 cos 75 is 0.464. Cool. And then we have this component here, which is going to be 1.793 sine 75. So 1.793 sine 75. Now that's the part, incidentally, that is affected by E, because basically it's the motion in that direction. To work out what the equivalent motion is on the other side, you would take this times it by E, so that's going to be times 0.464. So that's going to be 0.8. Whereas that component stays the same, that's 0.464. And then all we have to do is apply Pythagoras' theorem in trigonometry. So first of all, let's call this V2 for the velocity after the second collision. That would be so square that plus 0.464, square root the answer, oops, excuse me. is 1.053, and the angle, call that theta, so the inverse tan of 0.8, let's put that in brackets, 0.8 divided by 0.464 is 59 degrees. Okay, so do a little bit of reality checking now. So that second collision really killed off a lot of the speed, but then you'd expect that if the angle of approach is 75 degrees. So that's relatively normal. From 1.7 to 1.05, it's almost halved. Not quite, but you know, it's close to halving, which again is what you'd expect because E is actually less than a half. And finally, the angle here, 59 degrees, is less than the angle here, which is exactly what you would expect to happen. So that's that question done.